Well, I found a new resource, a new website to pull some information from, and I've used um, I don't know, I've used some of it. I forget. Oh yeah, this right here. I did some screenshots, and my first little video cast was about the plotting the rates of reaction from the enzyme catalase. Anyway, it's the website's mrgscience.com, and I can post it to the Google Classroom if you want me to. But I wanted to just kind of go over I don't know, what I do when I read these chapters, um, and what I expect when you guys annotate your notes. So, of course, I got to this from the Weebly site. Um, This latest one is topic 8, metabolism, cell respiration, photosynthesis. I just now noticed that this is a shape of a butterfly behind a leaf, which is pretty rad. I don't know. Anyway, 8.1, you basically are responsible for those four understandings and these four applications and skills. Um, and the guidance in enzyme inhibition should be studied using one specific example for competitive and non-competitive inhibition. Um, I don't think you should expect any more from IB of what they expect enough. So I don't think you should go above and beyond, and I think we're pretty good at knowing that. I'm always looking at the tables to fill out and to understand. So the first one here, anabolic and catabolic reactions. We know that anabolic builds, and conversely, catabolic reactions break down. And we have building of organic molecules in photosynthesis, as you can see here, and a breaking down of that organic molecule in cell respiration. And you know how photosynthesis and cell respiration are coupled. Um, one builds complex molecules and the other one breaks them down. One's endergonic and the other is exergonic. Endergonic requires an input of energy, whereas exergonic you get energy out of, so it produces energy. Um, and I, looking at that table and writing it down and understanding that and having that as a base is kind of expected at this level. When I go through, I see metabolic pathways. So this is just a very general substrate A. What do we have? Turns to substrate B, which turns into the final product. Of course, what's not listed here are the enzymes. You need enzymes for A to get to B to get to the final product. And as it reads here, that each arrow represents a specific enzyme. So that's that. I just made that point. Um, we found out that the induced fit model of enzyme action is better than the lock and key model of enzyme action because of the idea that it doesn't show an image down here. I was going to show an image, but it doesn't show an image. The idea that the enzyme is actually changing shape so to fit the substrate, whereas lock and key is a more of a rigid system where if the key doesn't fit, then it doesn't it's never going to fit, which is actually inaccurate when it comes to the current theory on enzyme action. um, Something about it, which is, I know we mentioned it when I taught enzymes last, but IB specifically wants you to know about activation energy and um, what enzymes do, um, what enzymes do to lower that activation energy. What you see here is a reactant. Without the enzyme, it has to get a larger input of energy in order for the reactant to turn into the product. In this case, it looks like a catabolic reaction where it is being broken down into 3 or more products. An enzyme is going to lower that energy by facilitating that meeting between the reactant, the 2 reactants, or the 1 reactant breaking apart. 2 or more, or 1 breaking apart. It really wants at topic 8, which is higher level. When I see bullet points in a chapter, I'm immediately going to write them down, and that says to me that that is an important topic to understand. So the mechanism of the enzyme action. So it's basically summarizing or outlining rather what happens when substrate meets enzyme. It's very important to know that enzyme plus substrate gets an enzyme substrate complex, and then that breaks down to enzyme plus product. And of course, seeing the double arrow, that is reversible. In the next video, I will speak about inhibition. So that is it for now, because I need to get a drink of water because my throat is sore. Okay, so next video on inhibition. Well, never mind. I will just tell you. Never mind. I've suddenly remoistened my throat. Anyway, inhibition is basically inhibiting the enzyme to work. Competitive occurs at the active site. So you can see when you have a competitive inhibitor, the substrate can't bind to the enzyme. Therefore, the substrate can't either break down or into more than one product, or it cannot form into one product if you are requiring 2 or more substrates to meet at that particular enzyme. This is one example in biology where it's kind of easy to understand. Competitive means it's competing at the active site. Non-competitive, which is down here, is not competing at the active site. There is an alternate site we call the allosteric site, which can attract an allosteric inhibitor, which will actually deform the enzyme so the substrate won't bind to it. And as it reads in the figure down here, the allosteric inhibitor combines with the allosteric site. Okay, that makes sense to me. And it causes the active site to change shape. So there's no, it's pretty straightforward when it comes to inhibition in enzymes. And inhibition is basically just inhibiting the product from being formed. In product inhibition it's amazing how living systems can communicate with each other, and as far as chemically, in order to save on resources and ATP, basically. So the first sentence here at the top, in product inhibition prevents the cell from wasting chemical resources and energy by making more of a substance than it needs. So if we go down here, you've got, I'm not going to sit there and read that to you, but you've got an initial substrate that combines with the first enzyme to make a product, an intermediate product, and then it does it again to make another intermediate product, and then it bumps into another enzyme which makes the end product. Now, right over here it says A represents a normal pathway with several enzymes producing intermediate compounds along the way. Now, B represents feedback inhibition. In this condition, a large amount of end product is present. The end product inhibits enzyme 1 in the pathway. So because the end product is being made, it is now combining with enzyme 1 to actually close the active site, so the initial substrate can't bombard into the first enzyme in order to make the first intermediate, the second intermediate, and finally more end product. It's a negative feedback loop. It's basically so living systems don't produce more than they need, or they produce more than they need, but then they stop. So they're not wasting energy. What else? There's a worked example down here. Um, you know, when I'm reading chapters, I will look at them. Maybe we'll do this in class. It does give the solutions, or in English, that's the answers. In English, that's solution. Um, so maybe we'll work this in class tomorrow. But I hope this has helped a little bit.